Light shows different colors depending on its spectrum. Conventional color cameras are manufactured to resemble the human eyes, which are exposed to the three colors of red, green, and blue. What will happen if subdividing these three channels of red, green, and blue? The technology of a hyperspectral camera aims at capturing detailed information of objects by taking more spectrum channels. Hyperspectral imaging is the next generation of color imaging which can capture dense spectral resolution for each wavelength. It means that the hyperspectral image captured allows to obtain the image data able to be physically analyzed.
Hyperspectral imaging can capture a high-dimensional information of spectrum. By doing so, a single-shot hyperspectral image means a three-dimensional volume of spectral information. Accordingly, the design and algorithm for hyperspectral imaging introduced demanding technical challenges, such as severely ill-posed optimization problem and large size form factor. Therefore, we made our effort to overcome such technical challenges by introducing novel design and algorithm for advanced hyperspectral imaging. We hope that our research can push forward current capability and applicability of hyperspectral imaging for the next generation of imaging devices.
Min-Hyuk Kim's research team of KAIST, by studying both of a hyperspectral camera and hyperspectral restoration algorithm, has developed the application algorithm where an effective hyperspectral camera system and hyperspectral image are used. Existing hyperspectral camera technologies have disadvantages of spending too long to take or having low accuracy in its system. The reasons behind them are, first, the camera system itself is complex, and second, the algorithm essential to restore images from the photos taken is inaccurate. The compact hyperspectral camera developed by Mr. Kim's team is able to restore hyperspectral image by analyzing the level of color dispersion generated by the prism installed in front of the camera. A subject has the two spatial axes and one spectrum axis of three-dimensional data, but the subject image taken is two-dimensional data with two spatial axes only, which makes it difficult to be restored into the original three-dimensional data. This research team developed a new optimization algorithm which can restore a subject's original spectrum by analyzing how the colors of the edge parts of the subject photo with the spectrum data projected are changing. A compact hyperspectral camera has the strength of being able to obtain hyperspectral data via the simple single shooting system. It has much simpler camera design than existing systems, but it can capture much higher levels of hyperspectral information. The first key point of this technology is to learn the prior probability of hyperspectral image using convolutional autoencoder, one of the significant deep learning models. An autoencoder model is a network one that learns the function of generating the same output with the input given. This nonlinear model is able to learn the data distribution of hyperspectral image more accurately than existing linear ones. Its second key point is to develop a new algorithm by applying the convolutional autoencoder learned to existing optimization-based restoration. This newly suggested algorithm is able to restore from input compressed sensing image the hyperspectral image having dense spatial resolution and spectrum accuracy. Having dense spatial resolution means the clean image of the objects inside of images and accurate spectrum. The image restored is able to be shown in actual colors.